Hey there, Stat200. This office hour we're going to be talking about something called sampling distributions. So sampling distributions, to kind of distinguish from probability distributions, which is what I talked about in another office hour, is that sampling distributions, we're not really concerned about individuals anymore. We're concerned about the mean, or the sample proportion. We're concerned about a certain statistic that comes with taking these samples. So, to conceptualize, what I'm talking about here is we have samples, let's say, for example, samples of size 50. So I took one sample of size 50. Say we're looking at income for people aged 30 to 50. And I took 50 people aged 30 to 50. I asked them for their income, got the average income, okay? And then I go ahead and do it again. I get 50, I do another random sample of 50 people, so 50 potentially different people. I find their average income. You see, now I have two means there. And I do this over and over again. I keep taking samples of size 50 and getting those sample means, right? Now I have a bunch of sample means put together, and they're all probably pretty similar. And I use that kind of sample means now to guess at where the population mean is going to be. Make sense? So let's go through some examples. We're going to talk about this and kind of see a few applications. So first question says, suppose we select a random sample of n equals 100 students and find that the proportion of students who said they believe in love at first sight is 0.43. Which statement is not necessarily true? Alright. There were 43 students in the sample who said they believe in love at first sight. Well, sample proportion was 0.43, sample size was 100, so if 43% of 100 students said they believe in love at first sight, that means how many students said they believe in love at first sight in the sample? 43. This one is definitely true. Has to be true. Alright? That one is necessarily true. Alright, second option. Based on the information provided by the sample, we cannot determine exactly what proportion of the population would say they believe in love at first sight. Well, we have a sample proportion, but if you took another sample of size 100, is the proportion definitely going to be exactly 0.43 again? Probably not. You know, it's not going to be it's not guaranteed to be 0.43 again. You know, you have a different set of 100 people, maybe 0.45 of them, 45 of them believe in love at first sight. It'll vary a little bit from sample to sample, right? So based on the information provided by the sample, we can't determine exactly what proportion of the population would say they believe in love at first sight, right? Because samples vary. They can vary a little bit. So again, this one is true. This one is true by necessity. P hat is 0.43. Well, P hat is the sample proportion, right? We have a sample here. We find that the proportion of students in the sample is 0.43. That's exactly what that is. Same thing. So obviously it's going to be the last option, but let's talk about why that is. P equals 0.43. Well, actually, it's kind of the opposite of the second option here. So we have a sample proportion, a p hat, if you will, of 0.43, but that does not mean that the population proportion is 0.43. Right? There's a variation from sample to sample, so maybe the true population proportion is 0.40. You know, you happen to poll 100 people who, on average, were maybe a little bit more believing in love at first sight. So that's why this one is the answer. Next one. A store manager is trying to decide whether to price oranges by weight, with a fixed cost per pound, or by the piece, with a fixed cost per orange. He is concerned that customers will choose the largest ones if there is a fixed price per orange. For 1 week, the oranges are priced by the piece rather than by weight, and during this time the mean weight of oranges purchased is recorded for all customers who buy 4 of them. The manager knows the population of weights of individual oranges is bell-shaped, with mean of 8 ounces and a standard deviation of 1.6 ounces. If the 4 oranges each customer chooses are equivalent to a random sample, what should be the approximate mean and standard deviation of the distribution of the mean weight of 4 oranges? Alright, so right off the bat, I'm looking at the first answer option here, and I know that many of you will be tempted to choose that one, because it's just everything multiplied by 4. Well, it's going to be the mean of 8 multiplied by 4, so I think many people are tempted to choose this. And 6.2 is close to 1.6 times 4, so many people are tempted to say that that is what it is. But not what we're talking about here. We're not talking about the mean of 4 oranges. We're talking about the mean weight of 4 oranges, right? We want to know the average weight of those 4 oranges. Okay? So right there, we know that it's not going to be this one, and it's not going to be this one. This one is to trick anybody who thinks you divide by 4. Not the case. So we're looking at something that has a mean of 8 ounces, right? Now he knows the population of weights has a mean of 8 ounces. So the sampling mean, the sample distribution mean will also have a mean at 8 ounces. Or let me rephrase that. The sampling distribution will also have a mean at 8 ounces. The only thing we need to determine here is what's the standard deviation. Does it remain 1.6 like that? Just like the individual standard deviation for a sample of 4 oranges? No, it will not. This is kind of the key concept this week. The standard deviation is equal to, let's talk about this more accurately. Okay. The standard deviation of the sampling mean, or the sampling distribution, is equal to the standard deviation of the individual object, so the individual orange standard deviation, divided by the square root of the sample size, n. In this case, that's 1.6 divided by the square root of 4. You see where I get those numbers? The 1.6 comes from right here. The 4 is the sample size. Remember, we're only looking at people who buy 4 oranges. So, if that's what we're doing, what's the square root of 4? 2. That's 1.6 divided by 2, which is equal to 0.8. Does that make sense? So, the approximate mean and standard deviation of the distribution of the mean weight of 4 oranges. So this is the distribution of the mean weight of 4 oranges, which is what clues you in that it's a sampling distribution. I should have said that before. So that's why that is the answer. The mean will be equivalent to the population mean, which the manager somehow knows, and the standard deviation will be the population standard deviation that's given divided by the sample size. Key concept right there. Let's move on. Based on the 2000 census, the proportion of California population aged 15 years old or older who are married is P equals 0.524. Suppose n equals 1,000 persons are to be sampled from this population, and the sample proportion of married persons, P hat, is to be calculated. What is the mean of the sampling distribution of P hat? Again, this is similar to before. What's the mean of the sampling distribution? It's going to be exactly the population mean. The mean of the sampling distribution is going to be the population mean, or the population proportion. Okay, so in this case, what's that going to be? That is going to be this one. So right here. I include this question because many people will take 0.524 and they will divide it by the square root of 1,000. And I see where they're getting that from, but that's not the way you do it here, okay? So don't be tricked. Don't be fooled. Because that'll get you something like this. And you'll see two answers that are similar and you'll say, oh, that could be totally plausible. But it's not. It's actually an easier question than you think it is. Mean of the sampling distribution is the population parameter. Alright. if the size of a sample, I think that should say simple, a simple randomly selected sample from a population is increased from n equals 100 to n equals 400, then the standard deviation of p hat will remain the same, increase by a factor of 4, decrease by a factor of 4, decrease by a factor of 2. Alright? Well, we could simply show what this will be. Right? So let's just say the standard deviation. Well, this doesn't make any sense, but let's just say that the standard deviation is 1 because this will help us visualize better how the standard deviation will change, right? So the standard deviation for p hat is equal to the standard deviation divided by the square root of n, right? So I'm saying for the sake of example, let's just say the standard deviation is 1. It doesn't make sense in this problem, but it's okay. That's not the point. The point is to look at what happens when we change the sample size. So if I have it as 100, that's going to be 1 over 10 or 0.1. Now I increase it. I say it's now going to be 1 divided by the square root of 400. What's the square root of 400? 20. What's 1/20th? Oops, 0.05. Don't forget that extra 0. That's pretty critical. 0.05. Okay. That's all I'm asking you to do there. Now you look at these two, and you say, oh, this one is half of that one. Now a fancy way to say that is it decreases by a factor of 2. When you say something decreases by a factor of 2, what we mean is it's half. So when you increase your population size from 100 to 400, the standard deviation of the sampling distribution, the standard deviation of p hat, will decrease by a factor of 2. Because if I look at the two standard deviations of the sampling distribution, this one is 2 times that one. Sorry, don't want to beat a dead horse. I wanted to just illustrate it. Alright, and last question. This one's kind of short because we don't go over too many new concepts. We just kind of talk about how when we're looking at sampling distributions, we are looking at a kind of closer together distribution. It's like a tighter distribution. Whereas before we're looking at individuals, it's all spread out. When we start looking at the sampling distribution, everything gets pulled together and we get a much more accurate representation of where the population parameter is. Alright, and finally, which of the following statements is correct about a parameter and a statistic associated with repeated random samples of the same size from the same population? Let's look at these 4 answer options and we'll talk about them. Values of a parameter will vary from sample to sample, but values of a statistic will not. Values of both a parameter and a statistic may vary from sample to sample. Values of a parameter will vary according to the sampling distribution for that parameter, or values of a statistic will vary according to the sampling distribution for that statistic. Alright, so this is a key thing here, and this is something I should write down in bright red. So here's what I'm going to do. I'm going to write it here. Parameters do not vary. Okay? This is a very key point. Parameters do not vary. Now, if you guys ever happen to go to if you go into statistics and you happen to go to a Bayesian statistics school, people will refute that. If that doesn't make any sense to you and you have no intention to go into statistics for a graduate school, you know what? Don't even worry about it. Don't even think about it twice. Parameters do not vary. what this is basically saying is, for example, if we're looking at mean heights for all American males, there is only, at one point in time, there is only one population mean height. There's only one possible population mean height at right this minute, because there are only a certain number of American male adults, and at this very instant, they have one single random height. Or, I'm sorry, they don't all have one single random height. They actually all have, the average is a single fixed value. You see? You can round up all the American men right this instant, measure them instantly, and you say, oh, okay, that is the population mean. One single value doesn't vary at that point in time. So that is the key to this question. This one says the values of a parameter will vary from sample to sample, but values of a statistic will not. That's wrong. Parameters do not vary. Statistics vary, right? Like I was saying before, statistics can vary from sample to sample. You get a sample of size 50, and you get their income, and you have that average income for that group of 50, and then you take another group of 50, a different group of 50, and they have a slightly different sample mean. That's statistic. A sample mean is a statistic. Okay? So values of a statistic will vary. Parameters won't. Values of both a parameter and a statistic may vary from sample to sample. What did I say? Parameters do not vary. Not this one either. Values of a parameter will vary according to the sampling distribution for that parameter. Again, parameters don't vary. Okay? Values of a parameter will not vary. Values of a statistic will vary according to the sampling distribution for that statistic. Yes. That's the only one, that's the only answer option that doesn't say that parameters will vary. Parameters don't vary. They do not vary. Okay? Important thing to remember. Alright. That's all I have for this office hour. As always, if you have any questions, please feel free to send me an email. You can always try to set up an appointment over the phone or via the virtual office. Please try to send me an email before giving me a call, because often I'm in the middle of something else and it's hard for me to talk at that instant, and then it gets harder for me to get back to you. But if you send me an email and say, hey, I'd like to talk whenever you're available, or you even give me the times when you're available, then I can work out and say, hey, yes, you can call me at this time. Or you can include your phone number if you're comfortable with that, and I'll call you back when I'm available. Okay? Good luck this week, and let me know if you need any help.